So last time we had a discussion. I'll continue from there. Uh, I'll also revise it a little bit, but uh, I'll not go to the previous slides now. Uh, Basically, we were talking about hypothesis testing with reference to regression, and we were talking about null and alternative hypothesis, uh, etc., etc. So I'll come to that, but before that, I just want to make a general statement with an example. Suppose there is a random variable x, right? And this x has a probability distribution, and we can think of this random variable to be there on the x-axis. By standardizing it, so we have converted this into a standardized variable, and we have put it on the x-axis. And here on the y-axis, we have density. So we are looking sort of frequency distribution, which we can call probability distribution, or in plain words, we are looking into how dense the values of x are at different levels. For example, this value of x has the highest density. It means that it occurs more frequently than other values. The values in the tail are not that much dense in both the tails. So height of the curve measures the density. If x is a continuous random variable, we can think of probability of x being greater than or equal to a certain value, small x, to be equal to the area under the curve. So this I'm talking in general, right? Then I'll come back to regression. So this random variable x has a probability distribution, and we can talk of probabilities in terms of areas. Probability is area under the curve, right? So that's the connect. Now, in case of this standardized x, you must have heard about normal distribution and standard normal distribution. Standard normal distribution. Standard normal distribution has a mean of 0 and a variance of 1, right? So the meaning of standardization here is nothing but shifting to another scale, shifting to a standard scale, right? So the way how we shift to a standard scale is by calculating the standard error and dividing the variable by its standard error, right? That's how
Sir, can you please let in some students are waiting, like in the room?
okay, right? So in this case, we have a mean at the center. If the distribution looks like I have drawn here, sort of normal, and t distribution also looks like this. So the mean is in the center, and the standardized value of the mean of x is 0, right? So because we have shifted x to a new scale, standard scale, on standard scale, for distributions which look like this, the mean is in the center and it is 0, right? And from there, we can move to the to values less than the mean, and we can talk about their probabilities, and we can move to the right of the mean, and we can talk about the values on the right side and their probabilities by looking at the area under the curve, right? So for example, if we take a value, for example 3, so 3 is here, and we can have a -3 and we can have a +3. On the left side, we can have a -3. On the right side, we can have a +3. And there is area under the curve to the right of 3, and there is some area under the curve to the left of -3, right? So there are two types of areas here. One is area under the tail, and another is area in the center. Area is a measure of probability. So when I'm referring to green area, it refers to some probability. And when I'm saying uh, the red area, let me color it. So there is a blue area. It refers to some probability. So what is this probability all about? I can write it like this, that probability of x being greater than or equal to -3 and less than or equal to +3 is equal to blue. And probability of x greater than or equal to +3 and less than or equal to, or let me call it only less than because I have included equal to sign in the first expression, greater than 3 +3 and less than -3 is equal to green. Right? So there are two probabilities, two areas, blue and green. With reference to regression, if I connect it to regression, I can convert this x into t. So we have a random variable x, we standardized it, and then we converted it to a t values, and then we are talking about not x, but t. So a value of t greater than -3 and less than +3 is in the blue area, and a value of and the probability of t taking a value which is greater than +3 and less than -3 is green. right? So we call this green area to be the p-value. This is a popular name, and p stands for probability, right? It's not that blue is not a probability, that's also a p-value. But when I'm referring to regression, there is something called p-value, and it means green area. Keep it in mind, area under the tails. And this, it means that every t value, for example, t is equal to 3, right? Every t value is associated, or let me not write this associated. Let me write every t value has a p value. So this is the statement I was trying to make, that there is a t value and every t value has a p value, and p value is area under the tails. P value is the area under the tails. So let me ask you, did you get this last point? Every t value has a p value, and what is a t value? In Because I just explained that there can be a variable. Now let me convert this x and everything into my regression counterparts. So there was a variable, not x, but beta 2 hat. So I was talking about a variable, random variable beta 2 hat, and then I converted it into a t, and then I'm talking about probability for a given t value being greater than or less than, it's not always like this. This is for one tail, so I'm talking about two tails, so let me write it in terms of two tails. So a t value greater than some value small x and less than some value y. I'm giving this arbitrary values x and y. T taking x greater than x, t taking a value less than some value y is nothing but area under the curve. And then let me change it here. It is already changed. We have a t here, and then we have a p value small p here. And now everything is according to our regression. So we have we had a beta 2 hat scale and we converted it to a t scale. We just put the t value. Let me change this x also. This is basically t, right? So these t values on the x-axis represent beta 2 hat, right? They can represent anything. They can represent any variable. So because we are talking about beta 2 hat, the regression parameters, the estimators, sorry. So we have converted one of the estimators, which is the estimator of the slope coefficient, beta 2 hat, into a t. And now we are talking about areas and probabilities, and how we understand this, I've just explained here. So I've explained you a few things here, right? What is a p value? How do we get to a t when we are talking about beta 2 hat, but we are talking in terms of t? How can we do that? Then what is standardization? So standardization in this case, let me write it in a bracket and let me write it uh, in red so you can see that this is important. So here t is equal to beta 2 hat, the value of the estimator, divided by standard error beta 2 hat. That's how we convert it. So that's a standardization, right? Because we have converted a beta 2 into a t by dividing it by standard error of beta 2 hat, right? So I'll talk a little bit more about standardization, but before that, I just want to ask you, apart from standardization, I'll explain a little bit. Did you get that every t value has a p value, and what is a p value? Please tell me, yes or no? Priyank, are you there?
Oh yes, sir.
Did you get it?
Oh yes, sir.
Okay. What about others?
Yes, sir, understood.
Okay. So according to green area, what values we could have? Area under the tails and okay, clear. All right. So if you have any question, you can ask. If you want me, all right. So that's great. Now that's what when I'm referring to T, I'm referring to standardized beta 2 hat or standardized beta 1 hat in regression, because there are two estimators we are talking about and their sampling distribution is what we are talking about. So I'm referring to beta 1 hat and beta 2 hat and their T values. And then now you got what is a T value, how we calculate it. I'll talk about standardization a little bit. And you got what is a p value. P value is the area under the tails. And because why did I refer to two tails? Because in regression we do a two tail test. That's why I refer to two tails. So I'm referring to one value 3, t taking a value 3, and I'm talking about areas under both the tails together, the green area. That's why I said green area, because we are going to do a two tail test. Had this been a one tail test, I would have drawn a graph like this. Only one value. And then I would have separated green and blue like this. So this is green and this is blue, right? Had it been a one tail test, I would have referred to one tail only, and area under the area under one tail, maybe right tail, maybe left tail, depends which test we are doing. So if we are doing a t test and a right tail t test, then I would have drawn a graph like this. It means we are doing a right tail t test. There is a t value and there's an area under the tail to the right of a value, which is called the p value, right? Now, Uh, okay, let me talk about standardization a little bit, then I'll come back here. What is standardization? It is, my drawing is not good. You have to bear with me here. Uh, so when I'm saying that beta 2 hat is equal to 233, and that is plus 233, and suppose 233 is somewhere here, and this is beta 2 hat scale, and then I converted it to a t scale. That means now I'm referring to, suppose uh, Let me make it an easy number. So suppose beta 2 hat is 200, and standard error beta 2 hat is 100. Then t statistic is going to be beta 2 hat divided by standard error beta 2 hat, and it is going to be 200 divided by 100, and it's going to be 2. So this value will be 2, right? And then uh, we have a t table. T table looks like this, that there are some degrees of freedom, and there is sample size. And t table, just I will show you the t table, but what does it do? It just connects uh, t values to probabilities. So if you have a t value, it will give you a probability, that's area under the curve. If you have a probability, it will give you a t value, right, for a given sample size, right? Now we will talk about t table. So we have a 2 here and a 2 here also, and I've drawn 2 somewhere at the wrong place. Let me correct that also. So when it's a two-tailed test, there is a green area. So 2 is a standardized value, and 200 was the raw value, right? And 2 is a standardized value, and they are both counterparts, and they are one and the same, except for the fact that 200 is on the beta 2 scale, while t is on a standardized scale, which is t. So this 200 could have been 2000. This 200 could have been 2000, and then this 100 could have been 1000, and still your t could have been 2. So that's what t, the standardization does, is that it adapts to any value that a parameter can take to some set of values, some small values which t can take. So t can take I mean, if for any t distribution, if you are coming to a value like greater than 3, probability is very low, right? Always. It's always the case. For if you take one condition, suppose I'm saying sample size is greater than 20. So sample size, if it is greater than 20, which is normally the case, and you are talking about any probability distribution, then if the t value is greater than 3, probability is going to be very low, like 0.05, less than 0.05, 5%. So there is only 5% area in the tails when t value is greater than 3, right? Or 3 is a big number. In fact, if it is greater than 2.5, right? So just by looking at the t value, we get a measure uh, of how large, of how much area is going to be in the tails, right? By looking at the beta 2 value, we have no idea whatsoever, right? So it depends on both these numbers, beta 2 as well as the standard error. So for a same beta 2 hat 2000, if the standard error is very less, then t value is going to be a big value and there is going to be less area in the tails. For a small b value, right? But even very small standard error, t value can be high. So there is some switching of scales and it depends not on beta, the value of beta 2 hat, but it depends on both the value of beta 2 hat as well as the standard error to make a t value big or small. Apart from all this discussion, if we take t value in isolation, I'm making a statement that if t is of a measure around 3 for a sample size greater than 20, which is normally the case, the probability p value is very low, right? So that's what standardization does, is that it standardizes a variable on a scale which is very well known. We have tables which talk about probabilities, and they have specific probabilities for specific values, right? For example, if t value is equal to uh, some number, for example 2.2, then there is a specific probability area under the tails for this value, which you can see from the table for a given sample size, n equals to say 35, right? So that's what standardization is. We make our value standard. Now, as far as interpretation is concerned, this also makes interpretation, understanding uh, these things easier, in the sense that when I'm saying t value is 2, I mean to say that 2 standard deviations to the right of the mean and 2 standard deviations to the left of the mean. So we understand that how far we are going from the mean. So mean is here in the center, and then we are going 2 standard deviations to the right of the mean, and we are going 2 standard deviations to the left of the mean, and then we are referring to the area under the tails, which is the green area, right? So why we say 2 standard deviations? Because you can see this 2000 means 1 standard deviation means 1000 and 2 standard deviations mean 2000. So when we are saying 2 t value is 2, that means 2 standard deviations to the right, 2 standard deviations to the left. We are saying 2000 to the right and 2000 to the left on this scale, beta 2 scale, right? So standardization helps in talking about distances from the mean to the right and to the left. So how far we are going, it depends upon how big the t value is. And when it has a specific value like 2, we say that many 2 standard deviations to the right and to the left, and then we are saying what area we are referring to, the green area. So that's what standardization means, and that's why we do it. We just want to adapt our uh, uh, estimator values onto a standard measure, which is t. In this case, there are many other distributions which are followed by some other estimators. Here in regression using OLS, we know that our estimators follow t distribution. So we know it from before as given. Uh, how do we know it? That's another matter. But we know that in regression, when we are using OLS in classical linear regression model, given the assumptions, given everything, we know that our estimators sampling distribution of the estimators beta 1 hat as well as beta 2 hat, they follow t distribution, and then we have to see how t distribution behaves to talk about areas in the tails, right? Now, coming back to this slide, uh, okay, let's come back to what we were doing. Let us revise it now. So we were talking about our hypothesis testing, and we discussed that there is a null hypothesis and there is an alternate hypothesis. And suppose we are talking about beta 2, and our null hypothesis would be beta 2 is 0, alternate hypothesis would be beta 2 is not 0. It's a two-tailed test because of the alternate hypothesis says it is not 0, so it cannot be 0 if it is negative or less than 0. It cannot be 0 even if it is to the right of the mean, right? So when we are making this type of alternate and null hypothesis, what we mean by this is that if null is rejected, that means our uh, alternate is true, which means that beta 2 has a finite value. That means x affects y. If beta 2, if null is not rejected, that means we go with the null, and that means beta 2 is actually 0. That means x does not affect y. That means there is no relationship between x and y. So it comes down to rejecting the null and not rejecting the null. And these are the only two situations which are possible. In the end of hypothesis testing, this is the only statement that we make, that whether we were able to reject the null or not. One more point to be added here, that if you are able to reject the null, it means that there is, of course, if you are not able to, if you are able to reject the null, that's what it is written here. If you are able to reject the null, I'm underlining it. If you are able to reject the null, it means your results are significant. Your results are significant, right? In other words, X significantly affects Y, right? That's why we call these to be tests of significance. Now, when it comes to tests of significance, when it comes to rejecting and not rejecting the null, uh, it depends on the p-value. Okay, let me take another slide. So rejecting and not rejecting the null, if p-value is less than or equal to alpha, we reject the null, right? So we reject the null means we know null is beta 2 is equal to 0, and we know alternative hypothesis is beta 2 is not equal to 0. So if p-value is less than equal to alpha, we reject the null. And what is alpha? Alpha is the level of significance. So what is level of significance? Now, the question is that how much is alpha, right? So p-value is will become lower and lower if we move to the tails, towards the tails. if we are moving towards the tails, the area under the tails is getting smaller and smaller, right? That means the smaller the area, the is getting smaller, and if alpha is 0.05, then we can reject the null when we have a big T value or if we are more deeper into the tails, right? So what is level of significance is basically telling us that what is that dividing line, what is that dividing line that will make us reject and not reject the null. So our test, we are testing a hypothesis that beta 2 is 0. We will be able to reject it and not reject it, and it depends on alpha, right? So alpha is the dividing line, because if p value is less than or equal to alpha, then only we are going to reject the null. So it depends upon what is alpha. So it comes down to alpha. What is alpha? Now, how do we say that alpha is 0.05? So in other words, alpha is 5%, right? What does this mean? It means that if the area under the tails is less than 5%, we reject the null, right? So p value is less than equal to alpha and alpha is 5%. That means if area under the tails is less than 5% or less than or equal to 5%, then we reject the null, right? Now, alpha is a predefined number. It depends on us to decide it. It depends on us, researchers, to decide what alpha is going to be. We decide how much alpha we want, right? It's not given to us. We can decide alpha to be 5%. In other words, to be 0.05. We can decide alpha to be 1%. That means we can call it 0.01. We can decide alpha to be 10%. We can, in that case, alpha would be 0.1. So it's our choice. Generally, this is the case that generally we take it to be 5%, 1%, or 10%. We don't take alpha to be 7%. Of course, we can take it if we want. 7%, 6%, 12%. We can, if we want, we can take it like that. Right? What are the implications? I will tell you. But in conventionally, alpha is decided to be 5%, 1%, or 10%. And it is completely up to us to decide what alpha you want to work with, right? All right, so coming back. So if alpha is 5%, then the rule is if p value is less than equal to alpha, in other words, if p value is lower than or equal to 0.05, we reject the null. This rule will remain as it is, only the value of alpha will change. So alpha can be 5%, it can be 1%, it can be 10%. And alpha is the level of significance, right? Alpha is the dividing line that makes us reject or not reject the null. So we have to locate alpha on our graph, right? So the question is, let alpha is 5%. And let us show it on the graph. What does this mean? It means that there is a line somewhere This line gives an area of 5% in the tails. So we have our green area. Of course, this is going to fall and fall and fall. So this line is going to come closer to the x-axis. This line also is going to come closer to the x-axis. So our green area would become smaller and smaller and smaller. It will become negligible. Of course, it will never touch the x-axis. So this is the line, suppose, dividing line that divides area under the curve into two parts. Area under the tails, 5%. Area in the body, in the center, 95%. So we have 95% blue area. This is 95%. And this is 5%, so 2.5% here and 2.5% here. On the right tail, 2.5% in the left tail, and 95% in the body. And this value is the green area is alpha, right? So green area is alpha, right? And then we have a t value corresponding to it, right? So what is that t value? That's what is important. It depends on sample to sample, sample size to sample size, because we can have different t values for the same 5% area under the tails for different sample sizes. Keep it in mind. We have different t distributions. Of course, the shape is same for all t distributions, but we have a t distribution for each sample size, right? So for any given sample size, we can make this dividing line. We can draw a t distribution for that sample size, and then we can make this dividing line that divides 5%, 95% areas, green and blue areas. And then we can see the table to check what is that t value, and we can write it here. So this is t scale, and we can write a value here. For example, 2.2 is the value, minus 2.2 plus 2.2 is the value. For example, in this case, when sample size is 60, t value is 2.2. That gives an area of 5% in the tails and 95% in the center, right? So for a given sample size, and a given alpha, there is a unique t value, right? So for example, I gave it 2.2. I mean, it may not be 2.2 for a sample size of 60. I have to see the table for that. But I'm just explaining you that there is a t value that divides area under the curve into two parts, 5% and 95%. So for a given alpha, there is a dividing line that divides the area into two parts, and that line corresponds to a t value. So as I said in the last slide, that in the t table, we relate for given n for given n, we can see area and find t value, and we can see in the table a t value and find the area, right? So that's the dividing line. Now, how does this help in rejecting and not rejecting the null? Do we have time?
So we have like 3 minutes.
All right. So okay, so let us stop here because you may ask questions. I will continue from here next time for in these 3 minutes. If you have any question, you can ask.
Yes, so just one thing. What would be our syllabus for CIA 1 considering that the test is on 27th?
Test is on 27th. Okay, so we have finalized it on 27th, right?
Yes, sir.
All right. So the syllabus can be up to standard error. Let's not include hypothesis testing.
All right, sir. Thank you so much.
All right. Any questions, anyone? No question? If you have any question in these, what we discussed today, please do ask. All right then. So I'll save this. Priyank, please send me the list of absentees.
Surely, sir. I think so. No one is absent, though I'll still send it.
Okay. All right then. So that's it. Thank you. Have a nice day.
Thank you, sir.